14.4, the change of concentration with time. The rate laws we have examined so far enable us to calculate the rate of a reaction from the rate constant and reactant concentrations. These rate laws can also be converted into equations that show the relationship between concentrations of reactants or products and time. The mathematics required to accomplish this conversion involve calculus. I do not expect you to be able to perform the calculus operations, but you should be able to use the resulting equations. We will apply this conversion to three of the simplest rate laws, those that are first order overall, those that are second order overall, and those that are zero order overall. Integrated rate laws. Using calculus to integrate the rate law for a first order process gives us the following expression. The natural log of the concentration of A at some time interval t divided by the concentration of A initially is equal to negative kt. Again, A sub 0 is the initial concentration of A sub t is the concentration of A at some time interval during the course of the reaction. And T, of course, is time. K is your constant. We can manipulate the equation to give us this form of the equation, or manipulate it even further to give the equation for first order integrated rate law, which is in the form of y equals mx plus b. So we have natural log of the concentration of A at some time interval t equals negative kt plus the natural log of the initial concentration of A. This is our standard equation now for the first order process. Therefore, if a reaction is first order, a plot of the natural log of concentration of A versus time will yield a straight line, and the slope of the line will be negative k. Sample exercise 14.7, using the integrated first order rate law. The decomposition of a certain insecticide in water follows first order kinetics with a rate constant of 1.45 per year at 12 degrees Celsius. A quantity of this insecticide is washed into a lake on June 1st, leading to a concentration of 5 times 10 to the negative 7th grams per cubic centimeter. Assume that the average temperature of the lake is 12 degrees Celsius. What is the concentration of the insecticide on June 1st of the following year? And how long will it take for the concentration of the insecticide to decrease to 3 times 10 to the negative 7th grams per cubic centimeter? We're given the rate constant for a reaction that obeys first order kinetics, as well as information about concentrations and times, and asked to calculate how much reactant, that is insecticide, remains after 1 year. We must also determine the time interval needed to reach a particular insecticide concentration. Because this exercise involves time in A and asks for time in B, we know that the integrated rate law is required. We're given K equal to 1.45 per year, T equal to 1 year, and initial insecticide concentration 5 times 10 to the negative 7th grams per cubic centimeter. So we're going to substitute the known quantities into the first order integrated rate law. We have here the natural log of the insecticide concentration at 1 year equals negative K times T plus the natural log of the initial concentration of the insecticide. We're going to solve this equation taking the inverse natural log of both sides to get rid of the ln here. And we have 1.2 times 10 to the negative 7th grams per cubic centimeter. So once again, this is the concentration of the insecticide at a time interval of 1 year. For the second part of the question, we're given the K value, 1.45 per year. We're given the initial concentration of the insecticide and the final concentration of the insecticide, and asked how long it's going to take to get to that final concentration. So substituting those values into the equation, again, we have the natural log of the concentration. We're not sure how long it took to get to this concentration, but this would be the concentration that is expected after a certain time period. We have negative KT. Again, the time interval is what's being calculated, and the natural log of the initial concentration. So we have the initial concentration of the insecticide, we have the final concentration of the insecticide, and we're asked how long it's going to take to get to this concentration, how long it's going to take to degrade until it gets there. So we solve this equation and get 0.35 years. Practice exercise. The decomposition of dimethyl ether at 510 degrees Celsius is a first-order process with a rate constant of 6.8 times 10 to the negative fourth inverse seconds. If the initial pressure of the dimethyl ether is 135 torr, what is the pressure after 1,420 seconds? Here we can treat pressure as if it were the concentration. Another example of a first-order process. Consider the process in which methyl isonitrile is converted into acetonitrile. This data was collected for this reaction at 198.9 degrees Celsius. So we have a plot of pressure versus time. And then if we plot the natural log of the pressure versus time, a straight line results. Therefore, the process is first order. And also we can deduce that K is the negative of the slope, 5.1 times 10 to the negative fifth inverse seconds. Okay, now moving on to second order processes. Similarly, integrating the rate law for a process that is second order in reactant A, we get the equation 1 over the concentration of A at time interval T equals KT plus 1 over the concentration of A initially. This is also in the form of y equals mx plus b. So if a process is second order in A, a plot of 1 over the concentration of A versus T will yield a straight line, and the slope of that line is K. Sample exercise 14.8, determining reaction order from the integrated rate law. The following data were obtained for the gas phase decomposition of nitrogen dioxide at 300 degrees Celsius. Is this reaction first or second order in NO2? Okay, we're given the concentrations of a reactant at various times during a reaction and asked to determine whether the reaction is first or second order. We can plot the natural log of the concentration of nitrogen dioxide and also 1 over the concentration of nitrogen dioxide against time. One or the other will be linear, indicating whether the reaction is first or second order. Okay, so to graph the natural log of NO2 and 1 over the concentration of NO2 against time, first we're going to prepare the following table from the data. So we've just taken our time, our concentrations, the natural log of the concentration, and also 1 over the concentration. If we refer back to figure 14.8, it shows us that only the plot of 1 over the concentration of nitrogen dioxide versus time is linear. Thus, the reaction obeys a second order rate law. So our rate will be equal to K NO2 squared. From the slope of this straight line graph, we can determine that the K or the reaction constant, rate constant, is 0.543 inverse molarity per second for the disappearance of NO2. Okay, so here's figure 14.8, and we can see that the linear relationship is this one, 1 over the concentration of NO2 versus time, indicating again that this is second order. Okay, so for practice, consider again the decomposition of NO2 discussed in the sample exercise. The reaction is second order in NO2. They give us the rate constant K, 0.543 inverse molarity inverse second. If the initial concentration of NO2 in a closed vessel is 0.05 molarity, then what is the remaining concentration after 0.5 hours? Okay, half-life. Half-life is defined as the time required for 1/2 of a reactant to react. Because the concentration of A at half-life, or T1/2, is 1/2 of the original concentration, then the concentration at time interval t equals 0.5 times the initial concentration. For a first order process, this becomes the natural log of 0.5 times the initial concentration of A divided by the initial concentration of A, or this can be simplified to T1 half equals 0.693 over K. For a first order process, then, the half-life does not depend on the initial concentration of A. For a second order process, we start out with this relationship. It gets simplified a little bit further mathematically, and finally we wind up with the relationship shown here. The half-life is 1 over K times the initial concentration of A. In sample exercise 14.9, we're going to determine the half-life for a first order reaction. The reaction of C4H9Cl with water is a first order reaction. Figure 14.4 shows how the concentration changes with time at a particular temperature. From that graph, we're going to estimate the half-life for this reaction, use the half-life from A to calculate the rate constant K. So here's the reaction in question and the diagram shown. We're going to extrapolate information from that graph. We're asked to estimate the half-life of a reaction from a graph of concentration versus time, and then to use half-life to calculate the rate constant for the reaction. To estimate a half-life, we can select a concentration and then determine the time required for the concentration to decrease to half of that value. Equation 1415 is used to calculate the rate constant from the half-life. So from the graph, we see that the initial concentration is 0.1 molar. The half-life for this first order reaction is the time required for the concentration to decrease to 0.05 molar, which we can read off of the graph. This point occurs at approximately 340 seconds. So solving equation 1415 for K, we have 0.693 divided by the half-life, which is 340 seconds, and we can calculate K as being 2 times 10 to the negative third inverse seconds. At the end of the second half-life, which should occur around 680 seconds, the concentration should have decreased by yet another factor of 2 to 0.025 molar. If you inspect the graph, you will see that this is in fact the case. So practice exercise, again, using equation 1415, calculate the half-life for the decomposition of the insecticide described in sample exercise 14.7. How long does it take for the concentration of the insecticide to reach 1/4 of the initial value?